So far, we've only been using two features, the width and height of the bounding boxes. But we saw that they're not good enough. A pencil like this can be confused with a clock, for example. Today, we'll introduce a new feature, which will measure how elongated the shape is. This will help to separate pencils from other items in a third dimension. Now, Ilya solved this problem on Discord. It was part of homework assignments 3 and 4. So we're going to use his code. And let me briefly explain how it works. He first computes something called a convex hole, the smallest convex polygon that encloses the drawing. He did it using the Graham-Scan algorithm. It's not the only algorithm that can calculate it, but Ilya used it and I think it's a good choice. It goes like this. First, it only considers the points, not the paths. It finds the lowest point and from there it calculates the angles to all other points and sorts them. Then, in order, new points are added to the stack again and again. But if the points are found to be in a clockwise order, the middle one is removed from the stack. Repeating this until the end gives us the convex hole. Now, Ilya used the edges of the convex hole one by one to construct oriented bounding boxes around the shape, and chooses the one with the minimum area. That's how he solved the problem. Scared? Don't be. Ilya did the hard part, and we're just going to use the end result. I also think that if you study his code, it won't take long before you understand it. Get it? Won't take long? Because we're going to measure the elongation. Oh, no. Gonna code, debug, and have fun. Coding with Radu. Coding with Radu. Gonna prototype and design. Coding with Radu. Coding with Radu. Let's code now. We're gonna implement the new feature using Ilya's help, who solved homework assignments 3 and 4 pretty much. I'm gonna give you this link in the description. Let's copy this code. And I'm also going to write it in a file called geometry.js. Let's go and put it inside of common here, create a new file, geometry.js. And I'm going to paste his code here, format it slightly, and at the top, let's write where this code belongs to originally. And I'm going to paste this link right here as well. And here we find all the functions needed by the algorithm. This returns the lowest point, and it keeps in mind that the y-axis goes downward. Then here the points are sorted relative to their angle. And here is the actual implementation of the Graham-Scan algorithm. The points are added to this stack right here, and then the stack is returned. There's also this helper function here that calculates the width and height of a box aligned to the hole in some way. These are all vector operations, and they should be clear if you've watched my prerequisite video. But basically, it finds out what is the left, top, right, and bottom, and then calculates the width and height using that. Ilya also returns these vertices here, which were returned back into original space. They're not really needed, I think, but it helps debugging, and you'll see, we'll make use of them. Now, this one is basically going to iterate through all the possible orientations and find the box that has the minimum area. And then everything is returned here like so. Two other helper functions here, one for getting the angle and one for calculating the distance. The squared distance actually, because Ilya only needs here the relative distances and there's no point in taking the square root anymore. It's a kind of an optimization. Now that's the code pretty much, and it looks good. But how can we be sure it's good? The only way really is to test it. We could write unit tests for it, but I prefer to debug visually. So let's go to our dataset generator file here. And now where we generate the image file here, I'm going to run Ilya's code, take out the vertices from the minimum bounding box. And here we need to pass an object containing points. So I'm going to flatten the paths and just take the points from there and make sure that you pass here this, it's required. And then with these vertices, I'm going to draw them with the red color on the canvas. Now let's save this and open a terminal. Go to the node directory. And here, let's run the dataset generator. Like so. And while it's doing it, we can check the progress here. And we can see now this rotated bounding box. But it's missing one of the lines there. Let me just stop this and fix it by passing the first vertex one more time at the end. So what I will do is I will create here a new array containing all the elements of vertices, and then one more time vertices of 0, the first vertex. Vertex is just a funny word for point. Now if we run this again and check what happens in the images, it's closed as we expect. But I would like to see also the whole, and just to make sure that whatever happens here is correct. So let me close this one more time. And in the geometry, I'm going to go here where the whole is also calculated, and I'm going to add it here. Let's save this file, and back in dataset generator, I'm going to also destructure here the whole that we are passing now, and I'm going to copy this one more time with whole here. And maybe let's put this color to blue. Let's try one more time. Now we can really debug what happens here and make sure that the bounding boxes and the convex holes are what we expect, really. While this is processing, let's go and implement our new feature using Ilya's code. So in feature functions, I'm going to import here at the top geometry. If it's undefined, I'm doing this check because we're going to need to also use this file on the web. And geometry might be there already. And now the feature name is going to be elongation. And what we do to calculate this elongation is take out the points by flattening the paths. And then we just get the width and height from Ilya's function here. As before, and we return here the maximum between the width and height divided by the minimum of the width and height. And now in practice, it could be possible that the width or height is 0 from the drawings. Like if somebody draws a perfectly horizontal line, then the vertical coordinate is the same for all the points, and then height is going to be 0. and then this is going to be 0. So typically what you can do in this case is wrap these like so and add the +1 to each of them, because it kind of makes sense if you think about pixels that it does have some kind of height, even if it's 0 from this vector point of view. And it's just one way that we avoid this problem. I'm not really sure if it happens here, but I was thinking about this division by 0. So anyway, this new function now we can add right here, elongation, get the elongation. And for it to work, we need to adapt our distance function in utils right here to use the third dimension as well. So we could do that, for example, like this, by just including here the difference on this third dimension, denoted by this 2 here. So 0, 1, 2 means 1, 2, 3. But it's nicer to write this in a more general way, so we don't have to do this again and again every time we add a new dimension. So let's remove this and initialize a variable called squared distance with 0 and loop through all of the dimensions of the first point one by one and add to this squared distance the difference on that dimension squared. And here we just return the square root of that squared distance, and now we don't have to bother with this function anymore. So let's try to extract these new features now. I'm going to go here and type node feature extractor JS. And now let's run our evaluation. And look at that. We went above the 50% mark. Quite a significant improvement here. Let's see the results on the web as well. So I'm going to go here and make a few changes. In viewer HTML, we need to import also geometry now. And I'm going to do it here under utils. I think it's a good place. And let's save the file and refresh the page. And something is not right because this input shouldn't be there. And if I open the console, I see there are some errors in geometry there. And I'm quite sure they are because this input is empty and it's giving a list of 0 points basically. And let's have a quick look here inside of geometry.js. There are sometimes used points from the first index, second, third index, at least. So we would need to have at least 3 points for this code to work properly. And we can do that in multiple ways. Maybe we could go here in viewer HTML at the bottom and only update what's on the sketchpad, only process that. For example, if there are paths and if they have more than 3 points. So here I'm writing the opposite and I'm saying return if it's not like that. So this would work here. There's no more error. But the problem is if we do draw something here and then maybe revert everything, it doesn't process anymore this empty page. So I would actually like to return 0 width and 0 height if not enough points. So I don't keep this update here. Instead, I cut it and I go in geometry.js in the function that calculates here the minimum bounding box, and I say paste, but only focusing on the points. And if they are too few, I will return now a width of 0, height of 0, and let's return the vertices and the whole, and I'm just going to return all the points. So points, points, like so. Now this should work again without an error here, right? And if I draw something on the input and I undo, it also changes, so nothing is a car in this model's mind. Now, this is much better accuracy, and also if we look at the column here and the row here, the pencils are doing really, really good now. So we got what we wanted. And let's toggle this output to see the chart as well. And this is quite confusing now, because we are having 3 dimensions, so we should plot that elongation also on the 3rd dimension. But it's overkill, I think, and soon we're gonna have even more dimensions than that, and what do we do then? Also, this decision boundary plot, it's not proper at the moment. It should be a decision boundary cube, not a rectangle like this one. But we could start slicing this cube somehow if we really want. Let me first actually remove these samples from here, because they are confusing for what I want to show you next. And I do that here in the chart options by typing height samples, set to true. And then for that decision boundary plot, in run evaluation here, I'm going to go at the bottom, and here it's doing the prediction with just 2 dimensions. So we basically get the same as only with the width and height here, because the distance function is implemented based on how many dimensions this point has. So to have a 3-dimensional plot, we need to add another value here. And it would actually require another for loop and passing here another dimension, but this will just be a set of images on top of each other, so we have to slice this cube somehow. And now I'm slicing it at the minimum elongation, and I could slice it in other parts as well if I want, but let's just see what we get here. And I'm going to run this evaluation again and refresh, toggle the output, and you can see the pencils are actually gone. But that can't be true, because pencils are being classified correctly, and they are even classified the best according to our confusion matrix here. What happens is that the slice that we are doing in this cube with the minimum elongation doesn't contain them. We would have to slice further away, maybe with the maximum elongation, since they are the most elongated shapes there. So let's try that. Put here 1 instead, regenerate the decision boundary plot, refresh the page, toggle the output, and everything seems to be pencils. If it's the maximum elongation, our model thinks that everything should be a pencil here. But there must be a place where it kind of contains pencils and something else. So let's try cutting this cube maybe in the middle, regenerate the decision boundary plot, refresh the page, toggle the output, And seems like even here everything is a pencil. Okay, let's go even smaller, maybe 0.2. Refresh the page, toggle the output, and now we see something like that. Basically, the pencils are creeping out somehow and being replaced with something else as we traverse this cube in the z-axis. But let's inspect the samples a bit too. I'm going to go to Viewer HTML and remove this hide samples. Let's comment it for now. And here, let's still focus on the pencils, but only those pencils that are incorrectly predicted. Let's refresh, toggle the output. And here are the incorrectly predicted pencils. But this decision boundary plot now is kind of useless because we don't really understand it anymore with the third dimension there. Like, these are all wrongly classified pencils, but some of them appear to be over this magenta patch here because they might be in somewhere close to low elongation. So if I would click something here, you can see this pencil is very fat, so to speak. So it's in that zone where there was no magenta at all, maybe. And that's why it's categorized as a house and not a pencil. This seems to be a guitar. It's also a little bit thicker. And all of these bounding boxes and convex holes look great, I think. Really good job, Ilya. What happens here? This looks interesting. This looks like a problem, but what I think is here is that there is actually a small point there that somebody drew. And in our system, if somebody makes a point, it's not going to be drawn because there is no thickness, basically. But it might be there. Let's inspect a little bit. So it's this 5078 image. I'm going to go in our data set JSON this time, and 5078 is here. Let me format this. And I actually see here the first path even. It's exactly the same point repeated twice. So I guess this can happen too. Basically, there's one path there that is small and it's not rendered by our software, but the calculations pick it up. So it's not really a problem with Ilya's implementation. Maybe it's a problem with mine, with my visualization. But I don't want to bother with things like this. So let's forget it's an issue.